Hi everyone, my name is Shriya Nandagiri and today we'll be looking at the genetic link between the SNCA gene and familial PD. To start off, I will introduce familial PD and then the SNCA gene, followed by a discussion of the different loci of this gene and how they contribute to familial PD. Lastly, we will look at therapeutic implications as well as future research that can be done on this topic. So starting off, what is Parkinson's disease? Well, Parkinson's disease is a neurodegenerative disorder characterized by the loss of dopaminergic neurons in the substantia nigra region of the brain. While the majority of PD cases are sporadic, meaning they come as a sudden onset and without a family history of the disease, familial forms of the disease account for approximately 5 to 10% of all cases and are associated with specific genetic mutations. Among these is the SNCA gene, which encodes alpha-synuclein, otherwise known as ASYN. ASYN is a small soluble protein, usually found in the presynaptic terminals of neurons, where it plays a role in neurotransmitter release and synaptic function. In PD, ASYN undergoes changes accumulating into insoluble filaments, or fibrils, that form Lewy bodies. These aggregates are central to the neurodegenerative processes in both sporadic and familial PD. Today we'll be looking at how specific mutations at certain loci of the SNCA gene influence ASYN pathology and function. These mutations that we'll be focusing on include the A53T mutation, A30P, E46K, G51D, and H50Q. So starting off with the A53T mutation in the SNCA gene, it accelerates ASYN aggregation, leading to early onset of PD symptoms. This mutation is prevalent in Greek and Italian populations and results in severe clinical outcomes and faster disease progression compared to sporadic cases. Its impact on ASYN structure and function highlights its role in promoting neuronal dysfunction and the formation of Lewy bodies. In contrast, the A30P mutation in ASYN slows fibrillation kinetics but impairs membrane binding, disrupting cellular functions crucial for protein clearance. This mutation highlights the role of autophagic dysfunction in familial PD pathogenesis, and as a result, therapeutic targets to restore normal cellular degradation processes and reduce ASYN accumulation are needed. Next, the E46K mutation alters ASYN's interaction with lipid membranes, promoting its aggregation and enhancing neurotoxicity. This mutation's resistance to degradation underscores its role in prion-like multiplication and the spread of ASYN pathology in PD. This highlights the need to find targeted therapies aimed at restoring membrane interactions and preventing protein aggregation. Similarly, the H50Q mutation enhances ASYN aggregation and disrupts mitochondrial function, worsening neuronal toxicity in familial PD. Its impact on protein misfolding and cellular toxicity underscores its role in disease progression, highlighting potential therapeutic strategies aimed at reducing the effects of mitochondrial dysfunction and protein aggregation. Last but not least, the G51D mutation alters ASYN's aggregation kinetics, forming unstructured aggregates and influencing its cellular localization. This mutation's mixed pathology resembles aspects of PD and multiple system atrophy. This underscores its diverse impact on neurodegenerative processes and necessitates further research into its specific mechanisms and therapeutic implications. So, understanding SNCA mutations provides insights into familial PD mechanisms and identifies potential therapeutic targets. Developing small molecule inhibitors to prevent ASYN aggregation, enhancing autophagy, and regulating ASYN interactions with membranes are potential pathways for therapeutic development. Gene therapy approaches targeting specific SNCA mutations may offer future treatments by correcting or compensating for defective gene expression, highlighting the need for future research into these therapeutic strategies. Future research should focus on things like high-resolution structural analyses of ASYN mutants, identifying biomarkers for early PD detection, and exploring gene environment interactions in PD pathogenesis. That is all for me. Thank you so much for listening, and I hope you all have a great day.